Good morning. My name is Abhishek Kalra. Thank you for joining this webinar today. I look after the technical and application part of the 3D printing business for Altim. Uh, Last month, we conducted the first webinar of the series of 4 webinars that we are doing, which was a general introduction to 3D printing. What are some of the capabilities? What are some of the possibilities? What are some of the limitations? For those of you who did not attend that webinar, it's available on YouTube. We'll send out a mailer one more time. But not to worry, I have some parts of that webinar, some portions of that webinar as a recap in this webinar. Today, the objective of this webinar is to focus more on beyond prototyping applications. Whenever we think of 3D printing, the first word that comes into our mind is prototyping. And most people sort of believe that 3D printing is only limited to prototyping. It cannot be used in other areas of manufacturing. The reason for that is that people do not have a lot of knowledge of materials, of some of the process capabilities, and some of the design capabilities that are being used in India as well as globally to make 3D printing work beyond prototyping. So today we'll show you some examples. We'll talk about some materials. More focused in the plastic space. We will do another separate webinar on the metal space, which will be the fourth webinar of this presentation, fourth webinar of this series, sorry. So before we move on, just a little bit about us. Altam Technologies is a 3D innovation platform company. What that means is that we try and solve most, if not all, of our customers' manufacturing problems. We have solutions from product design to end part manufacturing and beyond. So if you look onto the right side of your screen, appearing now, we have alliances with some of the top global OEMs of the world, starting from Dassault Systems, which is a very popular name in the CAD and PLM space. We are gold partners for Dassault Systems. Moving on, we are partners with MSC Software, which is a US-based company, which has simulation and analysis tools for things like multi-body dynamics, FE, CFD, even simulation tools for additive manufacturing. Then at the heart of our business is our 3D printing solutions. We offer 3D printing solutions for both polymers with Stratasys, which is a US-based company, and SLM solutions for metals, which is a German-based company. Moving further, we have alliance with a Luxembourg-based company called Artec 3D, which produces handheld 3D scanners, which can be used for reverse engineering, digitization, and inspection purposes. And to complete it all, today the world is moving towards optimization, towards saving weight, towards saving material. So we have a very interesting tool from a company called Estico, based out of Italy, which is a multidisciplinary optimization tool. We've been around for roughly 10 years now, and in the 10 years that we've been into existence, we have won several awards, as you can see on the left-hand side of the screen. The most recent one being the most innovative 3D printing company of India award by Frost & Sullivan in 2017. And I also feel a lot of pride to say that recently we were awarded as the best company in terms of customer advocacy across all Stratasys, Asia Pacific, Japan, New Zealand, and Australia partners. So we are very proud that we are able to help our customers and address to our customers' needs more effectively. Now let's deep dive into the core of the presentation. Yeah. So you will see on your screen now some of our customers. As you can see, we have customers from almost all disciplines, from education institutions to aerospace and defense companies, to automotive suppliers, to healthcare companies, to IT services companies, and even consumer good companies like L'Oreal and Marico and IFB, etc. In total, we have close to 300 plus customers, some with multiple solutions from us. So the agenda of this slide is for you to be able to see that what is the vast variety of people that are using 3D printing. Now, before we move further and deep dive into the more advanced applications, just for the benefit of the greater good, the people who do not know, what is 3D printing? Now, 3D printing is a very popular subject and a lot of people have a lot of awareness about it. But I'd like to start by saying that it's a manufacturing process, right? A lot of people ask me whether 3D printing is going to get into people's home. It is getting into people's home, but at the end of the day, it's a manufacturing process. Now, the process starts with a CAD file, something that you design on your computer, or something that you generate out of scan data, any digital model, basically in a 3D format, which is split into a number of layers or cross sections. And then the printer or the manufacturing system basically lays down each of these layers one by one to form a complete 3D object, as you can see from the image on your screen. So imagine a piece of paper being a 2D layer or a 2D cross section. If you stack 100 or 1000 of them together, it becomes a 3D object. That's essentially how 3D printing works. But now, when we talk about 3D printing, there are two terms that we hear. One is 3D printing, and one is a term called additive manufacturing. So, are these two the same? Most people will say these two are the same. Most people will say they are different. So if they are same, then why use two different terminologies? So this is my explanation of the subject. Your idea or other people's idea of this may vary on it. But the reason I want to put this across is that because this will act as a sort of as a base for the other next few slides to come. So like any other process in the world, whether it be a manufacturing process or any other generic process, let's take cooking for an example. So when you have to cook a dish, it's not just the process of the dish heating on a stove or a flame, but there's a set of things that go before it and a set of things goes after it. For example, cooking will start with selecting the right ingredients, chopping them or cutting them to the right shapes and sizes, finding the correct spices and ingredients with the correct balance, then putting them all together, then cooking it with a certain set of procedures. It could be baking, it could be boiling, it could be cooking in a pressure cooker, then serving it and garnishing it, right? Similarly, additive manufacturing is a chain of processes, which typically starts with the design. So of course, to be able to manufacture anything, you need design. Design is the most crucial part of it. And then theoretically, you could go straight from design and print the part or produce the part using 3D printing. But because 3D printing has a lot of geometrical freedom that it is able to offer, and theoretically you can manufacture any geometry that you can think of. A lot of work is happening in the design optimization space, which essentially means that you modify your geometry in a manner that it exploits the ability of 3D printing to create any geometry possible, and hence create a better geometry, which may be lighter, which may be more efficient, which may be able to consolidate multiple parts into a single one, so on and so forth. Now, to be able to do this, you need certain set of CAD tools. And of course, anything that you can design, you can print. But there was a very big loophole in this whole process is to be able to analyze the life of the part. The example that you see on your screen is a bracket from a jet engine. Now, it's very easy to design this bracket using some of the good CAD software available in the world. It's very easy to print this part using any additive process, but this part is to go inside an airplane in the engine. Now, if we don't know how the part will behave for an aircraft taking off and landing 30 times a day for 20 years, we are not able to use this part, right? So simulation and analysis and pre-processing is a very important thing which was missing in the past but has come now. If you recall, I was telling about that MSC software, one of our OEMs has tools to simulate and analyze the life, things like stress, strain, thermal effects of a 3D printed part, both for metal and plastic processes. Then of course comes the heart of this process, which is 3D printing. But then you can imagine that probably you will not use this part, print this part using a plastic process. Whereas something as simple as a cabin interior cover may not be used using a metal process. So selection of the correct 3D printing process, or in some cases, multiple 3D printing processes put together form a complete part. And then the final stage of this process is post-processing. Post-processing could mean finishing the part to desired surface tolerances, or post-machining the part to get the desired tolerances. And then you get the final part. So as you see, 3D printing is only a part of the additive manufacturing process, and the correct design, the correct simulation, and the correct printing techniques make for the success or the failure of the process. Moving further, right? So what you see on the screen are two images, one from a metal component, one from a plastic component. Uh, what you see is examples of design optimization where multiple parts are being consolidated into a single part and the designs are being made lighter and hence more efficient. So that's the kind of impact that additive manufacturing has. And that's what this capability to generate these kind of parts is what is moving 3D printing from a proto or a pre-manufacturing process to a manufacturing induced part process. Moving further, so today we are going to talk about plastics. In plastics, we represent Stratasys. Stratasys is a US-based company, currently 30 years into operations now. Some of the top companies of the world and in India are using Stratasys technologies for various applications. Within Stratasys, we have two technologies. First is called fused deposition modeling. Fused deposition modeling, or FDM, is probably the most used and the most hyped technology in the scope of 3D printing. But yet, today you will find FDM printers which are as cheap as probably 50 to 60,000 rupees. While those printers are good for hobby applications, the real work, which some of which you can see on your screen, whether it be aircraft parts that you see on the right hand side of your screen, or automotive parts that you see on the center, or aerospace part that you see on the right hand side, is being done because of the good process control of a Stratasys FDM system, which enables it to print every geometry that you can design correctly every time, as well as get the best mechanical and thermal properties of the part. So today we'll talk a lot about the FDM technology. FDM essentially works with thermoplastic materials in the form of a filament or a wire. This filament is fed through a hot nozzle. The nozzle heats the plastic to the melting point and it extrudes the layer one by one to create the object. As you can see on the image below the text. We also have another technology within the Stratasys portfolio, which although is more meant for product realism, to create multi-material, multicolored parts, but we also have some very interesting strong materials which can be used for end-use parts and tooling applications. We'll do a separate webinar on Polyjet, which will be the next webinar in the series, probably in about 2 weeks from now, where we'll show you some of the most exciting stuff that is possible with 3D printing that maybe many of you would have never even imagined of. Moving further, so where is 3D printing used? 3D printing can be used for a variety of applications, but I'll consolidate them into 3 core applications, and then everything else is sort of like a sub part of these applications. So the number one is prototyping, which is probably 50 to 60% of the market share of 3D printing. Next is an application called tooling, which is the fastest emerging technology in additive manufacturing beyond prototyping. Tooling is again split into 2 parts. First is tooling for manufacturing. As you can see the example on your screen, we have used a 3D printed part. We have used a 3D printed part as a composite sacrificial tool and created a carbon fiber duct from it. Or you could take tooling as a manufacturing aids example, where you use 3D printing to create jigs, fixtures, and inspection gauges. Tooling is probably one of the most exciting applications of 3D printing. Many people, especially in the manufacturing space, who started with 3D printing being used as a prototyping method, have jumped into tooling. I'll cover on tooling a little later. And the final one, which is still a little less, I'd say, because 3D printing is not a mass manufacturing method, is end-use parts. So when we talk about 3D printing as a manufacturing process or to create end-use parts, we are talking about low volume, high value applications. The example that you see on the screen is a part from an aircraft. A few years back, Airbus decided to make a flying hospital, and in order to do so, they were to restructure the cabin. And what you see on the screen is a duct, right? Now, typically this duct would be a straight line made out of aluminium, but because the cabin modifications had some equipment which sort of was too high for the ceiling, they had to create this bump Now, to create one part to go for tooling or to go for traditional manufacturing process for them was very, very expensive. Hence, they resorted to 3D printing. And what enabled them to do this was materials which are strong, materials which are aerospace approved, and materials which can fit the application. So we will show you some more examples going further. But in the general spectrum, these are the three applications that are being used in the manufacturing space. Of course, there are applications in the space of healthcare and in the space of consumer electronics, consumer goods that we'll cover when we do the J750 Polyjet webinar. But typically in the manufacturing spectrum, these are the three key players. Right. Moving further, even within prototyping, 5 to 10 years back when prototyping just started, it was only about form and fit. You have a CAD file, two parts, let's say a pen and its cap that needs to fit together. And you just print those parts together and check the form and the fit and you're good to go. But today, because of the advanced materials and because of the advanced processes, 3D printing is moving from form fit to function and product realism or styling together. So the prototype, the image that you see on your top, the headlight, is the image of a prototype from Audi, which is able to give them form fit, optical functional testing, as well as styling, because it's able to create multiple colors, the correct reds, the correct transparencies in the one part. And the bottom one you see is actually from one of our Indian customers, who is a helmet manufacturer who use different filaments of different colors from FDM to create the helmet. And because the material is strong, he's able to do things like drop tests and crash tests on the same proto. So same part is able to do form fit, same part is able to do functional testing, and the same part is able to do visualization or styling. Of course, we spoke about rapid tooling, and in the last slide I showed you some examples of tooling being used as a prerequisite to start a manufacturing process. Things like creating cores for composite tooling, things like creating patterns for investment casting and sand casting, or things like creating tools of injection molding using a 3D printer. But there's an other spectrum to tooling, which is manufacturing aids. So the top example that you see is assembly fixture from BMW, which BMW uses to put their emblems of the 3 Series, 5 Series on its vehicle. This is being used both in global BMW manufacturing facilities as well as in India. The advantage of this process is to create complex tools, but make them lightweight, make them ergonomic. So traditionally, this fixture would weigh around 1.5 to 5 kg, and a BMW worker would have to lift this part every 1 minute. Now, with the help of 3D printing, this fixture only weighs about 600 to 700 grams, and it's very easy for the worker to handle it. It makes the line more faster, and it avoids repetitive engineers. And whatever you see is a CMM inspection fixture. The bottom one that you see is CMM inspection fixture, which is being used to inspect the parts that come out of the manufacturing line. The reason why, complex surfaces which are very difficult to machine can be very easily created using 3D printing, as you can probably see from the image on the bottom. And the final one being manufacturing. So I have two very interesting examples on the screen. The top one is an example from Daihatsu, Japan, which allows its customers to go on the internet, design custom skins, and then they will print the part using FDM technology in a UV stable material so that it doesn't degrade in the sunlight and stick on the car. We have backed a very similar project with Mini Cooper in China, and one of our Indian customers, Mahindra, is also printing automotive end-use parts for more repair and refurbishment operations for their earlier generation cars. And the bottom image that you see on the screen is an example from Qatar Airways. On their A350 aircraft, they have close to 1,000 plus 3D printed plastic components, different 3D printed plastic components, which they fly with. The reason for that is that we have materials which are FAA approved and can be used as fit to fly parts. Moving further. So now let's see a few examples of where it's being used in the manufacturing process. So for the success of any manufacturing process, the most important thing is materials, correct? So we have some very interesting materials which make the most difficult of applications to come to life. So I'll tell, although we have close to 20 materials in our FDM process, we'll talk about 6 materials today. The first one is polycarbonate. Polycarbonate, although we don't call it as the most strong material, it's a very useful material because of its impact resistance, because of its heat resistance, and because of its durability. Most people like the example of the helmet that I gave you. That customer manufactures that prototypes that helmet using polycarbonate material. But we also have a lot of customers who are doing sheet metal forming tools, as you can see on your screen, using polycarbonate. So now this is not a mass manufacturing tool. This tool is probably able to bend about 1,000 sheet metal parts, but that is good enough for batch production or pre-manufacturing validation. We also have a lot of customers in the aerospace community who are using polycarbonate jigs and fixtures as well as end-use parts in aircrafts. Next one. One second. Next one is a very interesting new material that we have launched in our FDM family called TPU. TPU means thermoplastic polyurethane. This is a rubber-like material which has been recently launched on one of our more entry-level systems, which is the F123 platform. The industry, especially the automotive industry, uses a lot of rubber parts for applications like seals and trims, for bellows, for hoses, for firewalls. So now we have a solution for those kind of applications. This material is the strongest elastomeric material available through 3D printing across the industry, not just in the FDM process. It has a break of close to 600%. It's also fire resistant, so it can be used in high heat applications. Moving coming to Ultem, or chemical name polyethermide, is a material that we launched about 7 to 8 years ago, and probably that material changed. Okay, I think there's a display issue. Give me a minute. Okay. Are you able to see? Okay, fantastic. So, Ultem material, or chemically known as polyethermide, is a fire-resistant material. It's got great tensile strength. It's got great torsional strength. It's FAA certified, and some of you may or may not know this, that a lot of Ultem parts are flying in Indian-made rockets, Indian-made satellites, and Indian-made aircrafts that are being made by our DRDOs, our HALs, and the space agencies. We have another version of the Ultem material, which I'm going to talk about in a minute. But before that, we had launched a very interesting material just about 6 to 8 months ago, which is called carbon fiber reinforced nylon 12. This has got 35% chopped carbon fiber weight by weight, which makes for the strongest material in 3D printing in the world. As you can see from the screen, you can see a whole bike resting on a carbon fiber made stool. The US Air Force also used this material to create a landing jig for crash landing scenarios so that they don't damage the aircraft, which was a very interesting example. I'll share the case study via email. This material is also chemically resistant, so it can also be used for chemical chemical manufacturing processes. We have a little bit more to cover on this material in the later part of the presentation. Moving further, we have the bigger brother of Ultem 9085, which is Ultem 1010. Ultem 1010 has the similar properties to Ultem 9085, which is good tensile strength, good torsional resistant, fire resistant, but it's got a little better glass transition temperature of close to about 200 degrees centigrade, which is the reason why a lot of companies are using Ultem 1010 material to create composite tooling. We have some examples in the later part of the style. This material is also food safe, so it can also be used in food packaging applications as well as surgical applications. Okay, moving further, the last material of this list is a PEC based material that again we recently launched about 6 months ago. PEC again is from the same family as Ultem. Chemical name is polyether ketone. Now this is the cleanest material in 3D printing available, with outgassing almost at 0%. So it's a space grade material. Again, with very high temperature resistivity, with very high chemical resistivity. So although the two Ultems and the Antero is an aerospace material by definition, a lot of our customers are using it in automotive scenarios for things like welding jigs, things like compression mold tooling, things like injection mold tooling, so on and so forth. Moving further, I'd like to give you a few examples which I like to call as the tip of the iceberg examples. A few people who attended the webinar last time would have seen a couple of these. So now, what you can see on the screen is 30 radar housings that Stratasys printed for NASA, which were installed on the exterior of the satellite in 2015. Before this, never ever were even 3D printed parts being used inside a satellite, forget outside a satellite. So it was a major achievement. Traditionally, these parts were machined in aqua quartz, but because of the difficult geometry, it was almost impossible to create an efficient part using machining processes. So NASA resorted to 3D printing. Although the past part was heavily post-processed in terms of thermal insulation, in terms of conductive insulations, but it was used. An extension of that is a new material that will be launched next year, which is an electrostatic dissipative version of the PEC material that I spoke about in my last slide. Now, this enables these companies to create electrostatic dissipative parts right out of the printer, and hence saves them in doing a lot of post-processing. Most recently, this part was used by Lockheed Martin to create a docking cover for the Orion 2 project, for the Orion 1 project, and 100 plus parts using this project material will be used in the Orion 2 spacecraft, which is due to launch in 2021. And again, coming back to some of the Indian examples, even our own Indian Space Research Organization is doing some great work in FDM, including prototyping, including composite tooling, and including many end-use parts which are flying in our satellites. Moving further, now this example is something which is very close to our heart, though it's still a prototyping example. It's a very high-stress application. Now, I'm sure many people know about the Statue of Unity, right? It was a very talked about achievement monument that is being created in India. For those of you who do not know, the Statue of Unity is the world's tallest statue, standing at 182 meters high, almost twice as tall as the Statue of Liberty. Now, when the statue was inaugurated, a lot of people printed scaled down versions of the statue. But our journey with the Statue of Unity began few years ago, actually, when a company called RWDI, which is a Canada-based company which also has wind tunnel facilities in India and Kerala, actually used the Stratasys 3D printer to create a scaled-down wind tunnel testing model, the results of which were fed as inputs to the construction agencies, and hence the structure, some of the critical parameters of the construction was decided. If you can see on the rightmost image, you can see some black markers on the statue, which are actually sensors which measure the data during the wind tunnel testing. And here we were able to help creating the world's biggest statue. We will soon have a case study published in this, where you can see the actual time, cost, and effort saving that the customer was able to do with respect to FDM 3D printing. Now, a lot of people have myths about 3D printing, that, especially plastic 3D printing, that 3D printing cannot be used for high temperature, high stress applications. But the example I'd like to show you is from a rocket launch scenario. The component that you see on the bottom right side of your screen is an ECS duct that goes around the rocket to provide cooling to the critical avionics and electronics of the rocket. This part launches with the rocket and then separates with the delivery module. So now traditionally this part was being created by ULA in aluminium, as you can see on your screen. But what the concern of ULA was that it was quite heavy, very difficult to manufacture, very costly to produce. So they resorted to 3D printing, and they were able to replicate this metal part into a plastic part. As you can see, it's very light now. The gentleman is holding into his hand. The part or the process was strong enough to create parts which could undergo the thermal and the physical stresses that would fall, as you can imagine, on any part that is going into a rocket launch scenario. But as a production part, they were successful with this. And from the past 4 to 5 years, ULA has been doing a lot of such projects with 3D printing parts being used as a replacement of metal parts. And you can imagine that the amount of loads a part needs to take, which comes in the contact of a rocket launch scenario. So that sort of breaks the myth that 3D printing cannot be used for high stress applications. And ULA predicts that there was a cost reduction of 57% approximately, because they were able to reduce the number of parts in the assembly from 140 to about 16. So that's a very big achievement for 3D printing. Moving further, an example from the automotive shop floor. I see some of the people who have joined here are from the automotive scenario. So today in the automotive assembly scenario plants, a lot of robots are being used to do operations like water jet cutting, so on and so forth. Operations like water jet cutting and so forth. So what you see on the screen is essentially a end-of-arm robotic tool that is used to grab a carbon fiber sheet and cut it using a water jet process. Now, as you can see from your screen, this part is unnecessarily bulky. It has a lot of components that are put together to form this part. And what you see on the screen now is a 3D printed version of this part, which is much more lighter. The lighter the robot, the faster it moves, hence the process becomes faster. Now, what you also see on the screen is, because of the ability of FDM to create parts which are hollow from inside, they were able to create the vacuum and the pneumatics pipes from inside the part, hence making the part even more efficient and even more lighter. So this part weighs 1.4 kg as opposed to 14.5 kg, which is a massive amount of weight reduction and adds a lot to the speed of the process. Also, debugging or repair of the part in case of any damage becomes very easy. And the major advantage that Genesis got out of this was weight reduction and part consolidation. There's also a video of this available on the internet, which you can see. I'll send the link when we send the link to the recorded webinar. Moving further very quickly. Now, a lot of work is happening in the domain of metal to plastic replacement, even in traditional process and with 3D printing. So we are giving at Altum and Stratasys, we are giving a lot of importance to materials which can replace metals. And one of the more popular materials is nylon with carbon fiber. So, which is one of the strongest materials, as I told earlier, in terms of in 3D printing, with tensile strengths of above 10,000 psi, chemical resistivity, good elongation at break, good temperature resistivity of about 150 degrees centigrade roughly. And we have two solutions with respect to the carbon fiber world. One, because of its huge scope in automotive manufacturing, industrial manufacturing, even bicycles, we are seeing a lot of bicycle manufacturers replacing some of the components of end-use bicycles with carbon fiber material, and of course aerospace. So we have created two solutions, one towards the top end of the spectrum and one on a more affordable spectrum, which is a new machine that we have launched on our Photos platform. Photos, for those of you who do not know, is a production platform from Stratasys, but we have launched a version of our Photos 380 machine for carbon fiber. A lot of people in the tooling world and the jigs and fixture world are adopting this machine. So it's very aggressively priced, and if you're interested, we can speak further on this solution. And of course, on the other end of the solution is our robotic demonstrator, which is able to extrude the carbon fiber filament mounted with the extruder mounted on a 5-axis robot and a table, which is a 3-axis robot, as you can see on the screen. So this creates unidirectional composite parts, which means that the strength of the part will be almost same in all the axes, as well as it is able to create the part without any support structure. Though carbon fiber material of ours works with the water soluble support structure, for people who want to create very, very large parts, this creates a very big impact. Although this robotic solution is not, which was developed in joint venture with Ford, with Stratasys USA. This is not commercial yet, but we are hoping to make it commercial very, very soon. But carbon fiber is probably the most asked material that we have today, and as one of the more popular materials, then we can discuss offline or with respect to your needs. Now, moving further, when Stratasys started Stratasys started into the world of what we call as direct digital manufacturing or tooling application, our core application was investment casting, that is creating FDM parts and burning them out to create metal parts. But today, we feel that our flagship application is composite tooling. Composites is becoming a very, very important part of almost every industry, whether it be aerospace, automotive, sporting goods, or marines. And we are very proud to say that with the help of Ultem material, we are able to do composite. We are able to sort of fulfill the entire composite tooling family, starting from layup tools to machining fixtures to trim tools and from drill jigs. And the Ultem material has a heat deflection temperature of about 200 degrees centigrade. Hence, it can be very easily used in production composite tooling. In our DRDOs, our space organizations are using Ultem material to create end-use composite tools for aircraft and satellite applications. And you'll see some of the examples on your screen now. So this is a sacrificial tool created by McLaren for a brake duct, where you print the core and then dissolve the core in a chemical, and the carbon fiber wrapping is being used as a duct, or whether it be a motorsport application again with sacrificial tooling, or a very long 15 feet tool created for the belly of the aircraft for Boeing. This part was printed in multiple sections on our largest FDM machine called Photos 900. Or you can see an aircraft belly tool from Aurora, where this tool is being printed, the composite being wrapped over it and fixed onto the aircraft, and the aircraft is flying like that. So we can use it for production tooling and without having any worries about the strength. And similar example you can see from Dassault for the Falcon jet for the wing aircraft. So composites is a very, very important application in our portfolio, and we can further discuss on this with respect to whether you can use composites using this kind of solutions. And now, thank you so much for your time. There's a very interesting video that you may not be able to see because of the lag in the screen, but I'll send you a link. Is Ford using 3D printing in its production line, where it's creating strong jigs and fixtures or inspection parts. Thank you so much for your time.